Hello friends, welcome to my channel. Let's have a look at problem 2458, height of binary tree after subtree removal queries. In this video, we're going to share a treatment based on find each node's depth, height, and their cousins. So here in this problem, we need at most two cousins. So first, I'll read through the statement of the problem to digest the requirement. And then we share the idea and do the analysis. And finally, we share the codes. So first, the statement. We are given the root of a binary tree with n nodes. Each node is assigned a unique value from 1 to n. So this sentence is very important. Notice that the node values are unique, right? So we are also given an array called queries of size m. So we have to perform m independent queries on the tree, where the ith query we do the following. So here this is also very important. So we're going to remove the subtree rooted as a node with the value queries I from the tree. So it's guaranteed that queries I will not be equal to the value of the root, right? If we remove the root, so we get a null tree. So the requirement is to return an array called answer of size m, where answer I is the height of the tree after performing the th query, right? So here is a note. The first one is that the queries are independent, so the tree returns to its initial state after each query. So in other words, if we know for a generic value, if we delete that, we can compute the height of the remaining tree. So actually we essentially solve the problem, right? The second one is that the height of a tree is the number of edges in the longest simple path from the root to some node in the tree. So this node must be a leaf, right? So this is the second node. So here are some examples. So let's look at one. Look at example 2. Let's just check the query value 3. So if we delete this tree rooted as 3, so the height is still 3. So we have 3. So if we delete the node, the root with value 2, so in other words, we delete the tree rooted at 2. So then the height will be either from here to here, or here to here, or here 593. So the height is 2, right? This is a 2. So actually you can interpret the returns for other values. So let's look at the constraints. First, the number of nodes in the tree is bounded below by 2 and bounded above by 10 to the power 5. And the node value is in between 1 and m. All the values in the tree are unique. So this is emphasized, right? So length of queries is m, and m is bounded below by 1 and bounded above by mean of n and 10 to the power 4. A mean less than n, less than or equal to n is the for consistency, right? Or you can see interpret like this. So queries I is also in the range 1 and n. Another consistency assumption. Queries I does not equal to root I. In other words, we do not make the tree null. So with that said, we went over the statement. So next we are ready to look at the treatment. So actually the problem is marked hard for Leetcode, but if we analyze this carefully, this problem can be easily solved. So first, let's look at the idea. So I'm writing this idea into several steps. So here's 2 steps. So first, for each node, we could find 2 pieces of information. So one is the depth and the other is the height, right? So we're going to use D representing depth and H representing height. So the depth is the path length from the whole tree root to the node, and the height is the height of the tree rooted as a node. For example, still here if we have 5, right, in example 1, so it has depth 2, right, because from the root to 5 we have 2 edges, and it has height 1 because the tree rooted at 5 So the longest path is from 5 to 7. Its length is 1. So this is the first step. And the second step is that for each node, so we're going to find the two cousins if exists, right, with the same depth and with the largest height. For example, the node 5 in example 1. So the two highest cousins with depth 2 is node 5, so with height 1, in other words, itself, and node 6 with height 0. Or if we like, we can use node 2. It's also with height 0. So once a node with value v at depth d is deleted, then the longest path for the remaining tree is the path that passes the node's cousin at the same level with largest height h0, and the resulting tree has height is nothing but d plus h0, right? So d is the depth and h is the highest cousin height. So here let me show one example. So for example, in example 2, right, so node 3, this node is at depth 2, right? Its cousins at this depth with decreasing heights are, say, 2, right? Its height is 1. And 1 and 3 and 7 all have height 0, right? So after deleting this node, right, so it's deleting 2, then the remaining subtree has height that is 2, the depth, right, plus the highest remaining height. So this is 1, right? So because if it, the node we delete is 3, right? So after we delete is 3, so this is still highest. So the remaining tree has height 2 plus 1, that is 3. So here is a remark, which is a final detail. It's possible that the value to be deleted is not within the two cousin nodes with the largest height, right? For example, if I choose the two cousins 2 and 1, then what we delete is 3, right? For sure, we can choose 2 and 3. That's nothing different. So our plan is the following. So we can actually use sort or min heap when we find the cousins with larger heights. So let's implement both. So actually, this tool of treatment is just quite similar. So first, now I'm going to do split into steps. So here we get height and depth of each node. So as we explained the depth, so with the path length from root, the whole tree root to this node, and the height is the path length from this node to deepest descendant or S. So in other words, this is the height of the tree rooted at this node, right? So this is actually very simple. We can do this using recursive format. However, we need to store the depth information and height information. Let's do this. So we can use collections default dictionary. So here I'm going to use integer as the default value. So another piece of information we want to store is height. So collections default dictionary. So it's also integer, right? So for this, I'm going to write a worker to do this job, and then we just call the worker. So let's call it worker, right? So given the node and the start depth, so let's see how we do this. First, if not node. So this is the stop condition. So we're going to return -1. So we'll explain why we return -1. So next, so we are going to store this node value, so depth, that is D, right? And then let's look at the L worker node left. So then we are increasing the depth by 1. So similarly right, so worker node right, so D plus 1. And then we're going to set H equals max LR, then plus 1. So that's why we return -1 here. So if you can imagine, so if the node is a leaf node, In other words, it has no child. So the height should be 0, right? So in this case, the left will be -1 due to this condition. The right will also be -1. Then the max of L and R will be -1. So -1 plus 1 is 0. So that's the consistency, right? So with that done, so actually we can also record the height. So the height of node value, that is h, right? So here actually we have implicitly used that the node value in this problem is a unique value, right? So then what we're going to do is that, so we're going to return this h. So if we call this worker, so then we will get the depth and height dictionary. So you can actually print this out just for get some feeling, right? So we print this out. Node is not defined to mean mode. So let's see where node. I see here. Root D. So here's the starting level is 0, right? So we get the corresponding information. So this information will help us to retrieve the our task, right? So with that done, so now let's do get the cousins for each level, right? So let's copy this part out. So this is step 1. Now let's look at step 2. So step 2, what we're going to do is that we're going to find cousins at each level. So this is actually a very simple task. So let me use a default dictionary again. So but this time, so this time I'm going to use a list to hold the cousins, right? So this actually is very simple. So for value d in depth items, right? First we can retrieve the depth, as depth is d, right? And then that's what we are going to do. So cousins at this depth. So this is because of the container list. So this is the list, empty list at the very beginning. So append, because we want to find the node with the 2 cousins with largest height, and we just need 2 because we deleted 1, right? So and then so we're going to use a tuple, right? So value. So the value is used to track the node to be deleted, and the height, negative height, will be used to find the 2 largest height cousins, right? So this is the very routine. So after that, so for this one, so what we're going to do is that we can sort this this thing. So what we are going to do is that let's see, we can cousins let's see, cousins sort. So here with the sort, so now what we want to do actually is we can remain at most 2. So here we can do val length cousins is greater than 2. So we're going to do cousins pop. So this way of writing, so actually the sort is actually sorting at most 3 elements, right? So this is the constant time, we'll see. So with that said, so we are done for finding the cousins. So next we actually get the return. This is the 3rd step. So for this, first I'm going to initialize a result variable to hold the result, and then for value in queries. So first we get the corresponding level, right? This is depth, right? So value, and then we find the corresponding cousins, right? So it's cousins d, right? So this cousins array, at least length 1 because it can contain this node with the value itself, right? Then first I'm going to check one case. So if length of this cousins equals 1, right? It means that this node to be deleted have no cousins at this level d, and then the remaining tree will have a length d minus 1, right? So we're going to append d minus 1 to the result. So that's one case. So another case is that, so let's consider else if value equals the cousins, so the first one, and it means that the node, so the removed node has maximal height in this cousin or at this level. And then what we're going to do is we append the result. So then we will have d plus the remaining highest height, right? That is d minus thin s, the other one at 0, right? Notice that when we append the negative height. So here we should use minus, right? With that done, so let's consider another case. So another case is that the removed node does not have the maximum height in thin s. So there are two possibilities. So either the removed value not in thin s, or in thin s but with the smaller positive height. Either way, so we're going to append so d minus csn and 0 and 0, right? So because 0 corresponds to largest height negative, right? So with that done, so we finish the problem logic. We just need to return the result state. So this forms one solution format. So let's do a check. So here collections default so here is not cousins sort, it's cousins d sort. Cousins d if length cousins d. So let's do the check. Yeah, it passes the first example. Now let's look at the generic case. Yeah, it passes all the test cases. So this is the V1. So now I would like to modify a little bit here. So I want to introduce the use of min heap, so to remain at most 2 elements. So for this, let me copy this this part. I'm going to put it here, and I'm going to use this one as V1. So the V2 here, we want to introduce the min heap, and so we introduced it here at this place. But we want to remain at most 2 elements in the heap. So and also let's do this. Let's see. Let's comment this out. So here, notice that cousins d will be the empty list at the very beginning. So we want to make it a heap. So for doing this, we can do this: heap q, heap pop, heap push. So the things we are going to push as cousins and d, right? But the key for the min heap will be height value, right? So we also include the value in order to track the node to be deleted or track the cousins. So this is the one. And then here we want to add a if condition. Let's comment this line out. So if length of cousins d is greater than 2, what we are going to do is heap q, heap pop, cousins d. So notice that because the pop will always pop the min element, the min corresponding to the smallest height. So after the for loop, after the end, so we always have for this cousins d the two highest cousins. So that's it. But now we need to modify this here, right? So similarly, we get when we iterate over the queries, we get the d, the level and we get the cousins, right? And then we check if the cousins list is 1, so we do not change. So next we want to do some change. So here let's see, else if, so the removal value is in CSN first. So let's consider this case. The removal value is in the cousins, right? In the cousins list. You should interpret accordingly. So in this case, there are two possibilities. CSN, the first one, it corresponds to the node to be deleted. So in this case, what we're going to do is that we're going to result at D plus CSN 1, 0. So at the height. Another case is that CSN 1, 1 equals value. In other words, the remove value is a smaller one. So we're going to append D plus CSN 0, 0. This 2 else block corresponds to the case that the removal value is in CSN, right? So the other case is the removal value not in CSN, in the cousins. So what we're going to do is that we're going to result append. We want to pick the larger one, that is CSN 1, 0, right? And then we just need to return the result. So essentially the two actually are the same, but here one we use sort and the second we use min heap. But due to the length control, actually this sort is constant space. The reason is that constant time because we sort at most 3 elements. So with that said, we are ready to check the second version. Yeah, it's right because it proves that our typing is right. So now let's look at the generic case. Yeah, it passes all the generic cases. I guess that's about it for this problem. So here the main trick we are doing is that we are trying to use a recursion to locate for each node its depth information, its height information, and also we consider its cousins, right? So once we have a lookup table for this information, then doing the query is very straightforward. So with that said, I guess that's about it for this video. Thank you very much.